Example 8.3, a 1 kilogram copper rod rests on two horizontal rails, 1 meter apart, and carries a current of 50 amps from the bottom to the top rail. The coefficient of friction between the rod and the rails is 0.60, and that's maximum, and the magnetic field is angled. A, draw a free body diagram and apply Newton's second law to solve for the magnetic field. B, what is the smallest magnetic field that puts the rod on the verge of sliding? We want the magnitude and direction relative to the y-axis for this field. So this is really an optimization problem from calculus when we look at part B. So the first one is just setting up Newton's second law, and from that we get the magnetic field. Then the optimization problem is that we then take the derivative with respect to the angle to find what is that critical angle that puts it on the verge of slipping. So let's start putting this together. Is the rod able to start moving in this situation? In other words, we got to look at what is the magnetic force going to look like. So if we start to do the rod, I imagine that we have something like this. We have a rod. That's across these two rails. So here's my rails. And then I'm going to have my rod that's going to rest right across the top of this. So what we're seeing is that we have a magnetic field that's angled and it's coming out. But then I got to look at the current. So what is the current looking like? So the current is, let's say it's coming down this rail, and then it's going to go. No, we don't have to have current going there. All we have to have here is that we have to have current going through the copper rod like this. So what we have to do is we need to use the right-hand rule to determine the direction of the magnetic force. So if I put this all together with the right-hand rule, here's my magnetic field. I'm going to have a current going in this direction. So by the right-hand rule, I see here that I'm going to get a magnetic force in this direction. In other words, if the force is large enough, I'm going to get motion in this direction right here. And that's because I'm going to get a magnetic force in that direction. So we're talking about it being on the verge of moving, but at least we know that the magnetic force is then going to be in the right direction. So once again, if the force is large enough, the copper rod will accelerate. The forces that act on the rod are the magnetic force, of course. We're going to have static friction, and we have, of course, we have a normal, and I'm just going to say that I'll just say gravity. But of course, the normal has to be from the from the rails on the rod. So since the magnetic field is angled, then a diagram of the situation is going to show something like this. So I have my rail, and this is a side view, and then I see my rod like this. So when I'm looking at this guy, I know that if I set my, let's say I set my coordinate axis, I'm going to say that this is my y direction, and I'm going to have this being my x direction. So then if I start to look at my forces here, from the center here, I know that there's a magnetic field in this direction. And I know that I'm going to say that this is angled. The magnetic force from this situation then shows that it has to be at a right angle going like that. So if I look at the angle, this angle is then also going to be this angle, the angle of the magnetic field and the angle of the force are going to be the same. I have a normal force coming up, and that's to offset the, to help with the gravitational force. And then I have friction acting on this thing right here. So those are the forces that are acting on that rod. So now I want to convert this into a free body diagram. So if I look at this as a free body diagram, I'm then going to see this. I have my dot. I have a normal force. I have my mg. And then I have my magnetic force, but note that my magnetic force is going to have components. So in other words, I'm going to project this down here, and I'm going to get my magnetic force in the x direction. And then I'm going to project it over here, and I'm going to get my magnetic force in the y direction. And then finally, I have my frictional force here. And my frictional force, which is static and its maximum, that has to be the coefficient of friction times the normal. So now that I have my free body diagram, I'm going to then define my positive and negative directions. I'm going to say that this is positive, that's positive. So of course, any other direction has to be negative. Now let's write out Newton's laws. Writing out the Newton's second law equations, we then get the following thing. Here's our first equation. It's going to be, let's say, the forces in the x direction. So if I look at the force, I have the force in the x direction because the angle is measured relative to the x-axis here. That means that's the adjacent side, so that's got to be FB cosine of theta. Now you could see that friction is in the opposite direction. So I'm going to get minus the coefficient, maximum coefficient, times the normal. And because it's on the verge of slipping, this is 0. So remember, this is on the verge of slipping. So it's just about to start accelerating. Then I'm going to look at the second equation. The second equation then tells me that I have two components in the y direction. I have my sine, Then I have my normal going up, and then I have my mg of the rod, and that has to be 0. So that has to be static equilibrium. Now, if I write the details of this guy, then I'm going to have this. Writing out the details of f of b. Now remember, when I say f of b, I really mean that I'm writing this as ILB, and this guy is going to be at an angle of 90 degrees relative to the magnetic field. In equation 1, we get two equations and two unknowns. And the two unknowns here are going to be the normal and the magnetic field. We can now solve for the magnetic field. So I'm going to start with equation 1. So if I look at equation 1, I'm going to isolate the normal. And that's going to give me f of b cosine of theta divided by the coefficient of friction. Then I'm going to sub into equation 2. And that's going to give me, so if I look at this thing, you're going to see here that I'm going to get f of b sine of theta plus f of b cosine of theta of this term right here. And then my right side is then going to be m of the rod times g. So if I do just the algebra here, and I isolate this thing, so then isolating the magnetic field, I'm then going to get that f of b is then going to be IL times b, and this will be mu of s sine of theta plus cosine of theta divided into mu of s, the mass of the rod, times g. Or we can write that the magnetic field is then going to be IL mu s sine of theta plus cosine of theta, all divided into mu of s m rod g. That's our magnetic field expression right here. And that's part A. So now we just need to do the optimization problem. So if I look at B, to calculate the minimum value of the magnetic field, it is angle dependent and requires finding the critical point. So the question is, what is that minimum angle? So the minimum angle requires setting dB min d theta equal to 0 to get theta critical. So let's do that. So dB, I wrote minimum here. I shouldn't have, because it's not the minimum yet. And this guy is equal to 0. Now, if I do the algebra, note that there's a lot of constants. Only the denominator has angle dependence. So I'm going to factor out all of these constants. So if I do that, I'm going to get mu s, m of the rod, g divided by IL. And the only term I have to worry about is this mu s sine of theta, cosine of theta, 1, and that guy has to be 0. So in other words, we don't care about this. So if I take the derivative of this term, what do I see? Well, the derivative of this term then says that if I look at that, I'm going to have d theta of mu s sine of theta cosine of theta. So I take the derivative of the top minus the derivative of the bottom. So I switch the sines and cosines, with one of them being a negative sign when I take the derivative of the cosine, and then I get the term below squared. Now, what's important about this is that this is 0 right here, but this guy here, this is never 0. So that means I don't have to worry about the denominator. I just have to focus when the numerator is 0. Focusing on the numerator, the critical point has the condition of mu of s cosine of theta, which is equal to sine of theta. Or, by the way, should you be surprised? When I first calculated this, I was surprised, but that's the condition that you learned from your mechanics course of the minimum condition for something to slide. So if you had remembered that, you could have written that down right away. So if I look at this angle here, I now have that theta critical is then going to be the tan inverse of mu of s, which is then the tan inverse of 0.60, and I get an angle of 31 degrees, and that's our critical value right there. So now that I have the critical value to get the minimum field, all I have to do is substitute it back in. So to solve for B minimum, we need to then sub theta critical into the B field expression. So I'm going to get B minimum, and then this will then be IL, and I'm going to get mu S sine theta critical cosine of critical divided into mu S m rod G. So if I plug in my numbers, I'm going to get 50 amps times 1 meter times 0.60 sine of 31, cosine of 31. Then I'll get 0.60 times the rod's mass, which is 1.0 kilograms, times g, which will be 9.81 meters per second squared. And if we compute this, we get a value of 0.10 Tesla for the minimum magnetic field.